Hi everyone, welcome back to the afternoon session. My name is SungBin Lee, who is going to be the session chair this afternoon. And the first talk of this afternoon will be given by Professor Gang Chen, and he will be talk about the semimetal, Luttinger semimetal, and the quantum spin ice interplay. Let's welcome him.
Thanks very much. First of all, let me thank the organizer for inviting me to this very wonderful workshop. And I have learned a lot from all these speakers and other attendees. So this talk is about some interesting title where Luttinger semimetal meets with a particular spin ion state in this Pyrochlore family. So I guess this talk I got this talk in somewhere else, but let me just briefly introduce my little small theory group on strongly correlated matter. We had two graduate students. One of them have actually transferred to UC Santa Barbara, and two postdocs right now. One just joined last year. So these are some recent small projects in the group. They're very random. We're doing a lot of random small little things in different topics in condensed matter physics. So the outline of the talk is as follows. So first, give an introduction to Pyrochlore iridates, and point out the strong spin-orbit coupling and the electron collision in this family of material. Point out the microscopics of this Pyrochlore-Pr2Ir2O7, where the conduction electron and the local moment interact with each other, how they interplay between each other. And then I talk about the magnetism-induced wire nodes, symmetry-protected Dirac nodes, and magnetic control of the topological band structure properties. And the summary of this talk is in this plot, which I will explain what's the meaning of this plot. So this work is in collaboration with Shiping Yao, who is my graduate student, and the paper is actually on PIRX today. You can find the online version. Right? So these are the publications starting from 2012 with Michael Hermley when I was a postdoc there. So this is the very well-known schematic phase diagram of the interplay between correlation. This is the correlation axis, and this is the spin-orbit coupling. So when there is no correlation, there is no strong spin-orbit coupling. So the system will be a simple metal or trivial band insulator. So if you turn the correlation, you can localize the electron, you can form these motor insulators. A physical example would be, a famous cuprate high temperature semiconductivity, the model state of high temperature semiconductivity. So on this axis, if you keep the correlation to be weak, but at the same time you increase the spin-orbit coupling, you can obtain various other interesting things, which is the main theme in the last decade of the hard condensed matter physics, which is these topological materials. The topological insulator, the wires and metal stuff. These are tantalum arsenide, bismuth, selenium, mercury, telluride, quantum wells. So we are interested in this regime, where both strong spin-orbit coupling and the strong correlation are present. So there has been a lot of interesting theoretical ideas. And also a lot of materials in this regime, and the interesting phases has been proposed, such as topological insulator, topological motor insulator, spin liquids, multipolar orders, axion insulator, wire semimetal, and other very exotic things can happen in this regime. So this regime is not really just of theoretical purpose. There are lots of materials. If you go down the periodic table, the atom become heavier. Heavier means the spin-orbit coupling becomes strong. When spin-orbit coupling becomes strong, spin-orbit coupling comes into play, and sometimes, for these 5D and 4D electron bands, usually the bandwidth is usually large. But when spin-orbit coupling enters, spin-orbit coupling will split these very large bandwidths into multiple subbands, and then each subband has a reduced bandwidth. So effectively, the correlation effect has been enhanced because of the suppressed subband bandwidths. So that explains why we are interested in these 4D, 5D materials such as iridates, osmides, resonates. This material has very strong spin-orbit coupling at the same time. Because of spin-orbit coupling, the correlation effect is enhanced. So that's the regime where the interplay between strong spin-orbit coupling and strong correlation play a role. Likewise, in these even heavier, like 4F electrons, with rare earth materials, spin-orbit coupling even stronger. This correlation effect is dominant. So this is a natural place to explore these physics over here. So this is not just a theoretical study. This is both theoretical and experimental converge at the same time. So now we turn to this family of material, which is called a Pyrochlore iridate. So this is actually a natural place to study the interplay between strong correlation and strong spin-orbit coupling. In other words, strong topological phenomena in the presence of strong correlation. So in this family of material, both this rare earth and the iridium atom from a lattice called Pyrochlore, which we have seen many times in this workshop. And if you vary rare earth atoms, because there are so many rare earth atoms, you can change the rare earth atom from holmium, diplusium, terbium, gadolinium, europium, and to praseodymium. So there is a change of this physical property. And almost all of them experience a metal inside transition around 120, 140 Kelvin, and with magnetism turning on. So there is a metal inside transition with magnetism, with the emergence of magnetism for most of the material except this guy, except the praseodymium, which remain metallic, and most of the time it's disordered. So although the system has local moment from the rare earth side, but this local moment remains disordered most of the time. And the conducting electron, which from this iridium side, remain metallic all the way. This is very different from the other guys, where there is always a metal inside transition with some magnetism from the iridium side. Yeah, so let me review some histories. So Leon Balance and Pessin, Dima Pessin, with a visiting scholar fellow at the KTP. At the time, they wrote this paper, very interesting paper. They cook up extended Hubbard model, include the spin-orbit coupling and the correlation. They propose some idea of propose this notion called the topological motor insulator. So this is a very exotic phase. This is actually a quantum spin liquid, a particular type of U1 quantum spin liquid, where there is a non-trivial electromagnetic response for this particular U1 quantum spin liquid, where this band structure of the spinons is topological rather than the trivial band structure for the fermionic spinons. So they propose this state, but this certainly is a very, very beautiful idea, but does not really apply to this family of material, because this family of material all develop magnetism. So later on, Shen Gangwan from Nanjing University and his collaborator, Tony Ashman Vishwanath and Sarasov from UC Davis, they studied the magnetism of this family of materials very carefully. And in this first diagram, as they crack up Harvard U, in the ab initio calculations, with a certain set of magnetic order, they find that there is a regime that they quoted as a Dirac metal. Really, because of historical reason, this is a Wisen metal. They call it the Dirac metal. So they found that the band structure of the conduction electron of the iridium 5D electron has been reconstructed by the presence of magnetic order. So they find that there is in the Fermi level, there is this point band touching. So this valence band and conduction band touch at the discrete points, and these discrete momentum points are called Y points. And these Y points come in pairs with plus or minus chirality associated with Y nodes. And in this important paper, the most important result in this paper is the observation, is the theoretical observation of the Fermi arc surface state connecting the projection of the Y nodes of different chirality onto the surface of a chunk of material. So this is the non-trivial surface Barr correspondence. So that was emphasized and pointed out in this great paper. So later on, many interesting works about the iridium physics, particularly Yang Kim and Lucia Savary, and Bongjong Yang and Wu Gongmo, and many others experimentalists like ZX Chen, Takura, etc. So today I'm going to focus on this material, which is very exotic. Remain metallic and disordered most of the time. This per se want to understand that. So this material was studied actually more than 1 decade ago, before the idea of this strong correlation in topological physics. So it's before that. So the system demand for this relativity and susceptibility and heat capacity measurement, there's no signature of magnetic phase transition. So there's no ordering anything feature. It's completely featureless actually. If you apply magnetic field along one direction, so as you cool the temperature, so this red curve is 0.5 Kelvin. This blue curve is much lower temperature. So there is a force order like a metamagnetic transition as you increase the magnetic field. So this is the metamagnetic transition for field along one line indicates the system has some strong magnetic anisotropy along this direction. This really suggests the system is in so-called 2-in-2-out spin ice state. The local moment of the local moment of presidium, local moment is fluctuating within the spin ice manifold 2-in-2-out. And you apply field along one direction, you pin one sublattice to the one direction. So there is a first order like metamagnetic transition. Yeah. Yeah, it's cubic. I don't think there is any there is a structure transition. I don't think there is any structure transition. No. Yeah. So this this material can have single crystal samples, can be well cleaved along one plane. So as a result, you can doing angle result for the emission measurement. You can see the band structure, and turns out they can observe the presence of this criticality band touching at the gamma point, and consistent with this DF calculation by Chen. So the DF calculation has a much larger bandwidth than the experimental one because DF calculation usually do not include the correlation effect. If the correlation effect is included, the bandwidth, the overall bandwidth will be suppressed. But the presence of this criticality band touching at the gamma point will be preserved. So this thing is modeled by a so-called Luttinger model, and that's why it's called a Luttinger semimetal. And this each band in the system it has twofold degeneracy because the system has inversion and time reversal. At high temperature, time reversal is preserved, inversion is preserved at high temperature. So each band is twofold degenerate, and this conduction band and variance band touch at the gamma point, and this band touching at the gamma point has a fourfold degeneracy. Right? So this fourfold degeneracy corresponds to this gamma 8 representation of the cubical group. So this band touching, as a result, is protected by the crystal line symmetry. So it's protected by the cubical crystal line symmetry. So this is the example of crystal line symmetry protected semimetal. So the parent state of the conducting electron is this crystal line symmetry protected Luttinger semimetal. Yeah. So that's the angle result for the emission measurement. They found this criticality band touching at the gamma point. Now many other people like Ugok, Sabari, and Yongbaek Kim and Chen Xu, they studied the correlation effect because the vanishing of density of states near if you tune the Fermi level right at this band touching point, the density of state is vanishing because criticality band touching in 3D has vanishing density of state. In 2 dimensions has a constant density of state. So the Coulomb interaction is not completely screened. So the Coulomb interaction is partially screened. That may lead to. You could have, yeah, sure, you could have inside. But if it is there, it is there, right? Yeah. Yes. Yeah, thanks for the comment. So that's the angle result for the emission measurement, which measures the conducting electron band structure, right? So apparently there are some other sample has been made very recently, and actually they develop magnetic order if you change the stoichiometry a little bit. And because the system developed, some sample develop magnetic order, if you change the state geometry, and it can be measured by neutron, neutron diffraction measurement. So neutron and this split heat measurement, they see this lambda peak transition at 1 Kelvin, and neutron diffraction see this particular magnetic order in the spin ice manifold. This is spin ice order. The system order in a 2-in-2R manifold, but this particular 2-in-2R manifold break translational symmetry. So the magnetic cell is twice larger than crystal unit cell. So this is neutron measurement. The reason why the system develops magnetically is because after you change the state geometry, the Fermi level is shifted up and down. So the induced RKKI interaction is different for different samples. And that's why some material tends to develop some sample tend to develop magnetic order. So that's the neutron diffraction measurement. So the material is rather complex. As a conduction electron has local moment, conduction electron doing something very interesting, and local moment also doing something very interesting. Right? A lot of interesting physics are going on in this material. So let's focus right now, for the time being, let's focus on the local moment, see what's the understanding on the local moment physics. So as I said, this local moment, the percent local moment from so-called 2-in-2R spin ice manifold. So this is an example of spin ice in diprosium titanate, where they see this polyentropy due to the 2-in-2R spin ice degeneracy. There is extensive degeneracy for the classical spin ice, because as you cool the system down to very low temperature, the system do not know which 2-in-2R state to be selected. And then they just normally fluctuate within this 2-in-2R spin ice manifold. There is the extensive degeneracy, which is estimated by Pauling and has been measured in this material. So this is the classical spin ice where the spin is treated classically. So the suggestion for this system is as follows: because the system sometimes remain ordered, sometimes become disordered. The local moment sometimes, most of the time is disordered, and sometimes become ordered from this neutron scattering measurement. So that means the system, local moment system, is proximate to a quantum phase transition from some kind of disordered state where the spin are strongly fluctuating to an ordered state, and the system is close proximate to this quantum phase transition. So what's the nature of this disordered state? As I said, the proximate magnetic order that observed by this material is observed by the neutron's diffraction is this 2-in-2R the spin ice manifold, spin ice order. So and this metamagnetic transition indicates there is 1-1 spin anisotropy. So a natural guess is this proximate disordered state is going to be a U1 quantum spin liquid of spin ice type. So if one assume that one can study the instability of this state and ask a question whether one can predict the right-hand side. So by studying the instability of this U1 liquid, can one produce the right magnetic order that has been observed in this system? So this is the work I done by myself in this long paper. So the idea is this transition, if they exist, there must be a so-called confinement transition. This is called a confinement deconfinement transition. So as I said, this state is a U1, a three-dimensional U1 particle spin ice, U1 quantum spin liquid, and in this state there are spin-on magnetic monopole, gauge photon excitations, and in the deconfined phase, in the U1 spin liquid phase, these spin-on are deconfined. The spin are strongly fluctuating in the 2-in-2R spin ice manifold. But if imagine you flip one spin, you create a defect tetrahedrals, and you can, because the spin are strongly fluctuating, you can actually separate these defect tetrahedral by arbitrary distance without costing too much energy. Because the spin along the pathways are strongly fluctuating, and this string connecting these defect tetrahedral have no tension. You can fluctuate this string arbitrarily. In other words, this is actually Xiaogang Wan's example of a string at condensed phase. The end of this string is the end of open string is a particle, and the string is strongly fluctuating. The closed string are strongly fluctuating. They give rise to this emergent U1 gauge photon. This is another way of understanding it. But in this U1 spin liquid phase, the spin-on are deconfined. because all the spins along the pathway are strongly fluctuating. It costs only finite amount of energy to separate these spin-ons to arbitrary distance. This is the spin-ons, and this is gadget photon, and this is another particle which is called a magnetic monopole. Some people call it electron monopole because of there's confusion in the terminology in our field. So I will stick to this name of magnetic monopole. This is very different from the spin-ons. Spin-on has this classic analog of a defect tetrahedral, but magnetic monopole does not. So what is magnetic monopole? So yeah, so you carry fractional spin quantum number. Imagine. Yeah, imagine, it may be easier to just think about some XXZ model. Then you have global U1. So then this global U1 symmetry has been fractionized if you consider spin-on excitation. Each spin-on will carry 1/2 of this kind of excitation. Yeah. Now this is the global U1. If you talk about lattice symmetry, spin-on can carry fractional lattice quantum number of translational symmetry. Yeah, so the deconfinement, or fractionalization, deconfined naturally lead to fractionalization, but fractionalization, can be manifested explicitly in the symmetry. Deconfinement and the symmetry, they are two different concepts, but you impose symmetry on the deconfinement or fractionalization. These fractionalized particle will carry fractional quantum number of the symmetry, and then this has a strong experimental consequence. This is very similar to the context of fractional quantum Hall effect, where this if you do not have global U1 charge conservation, so the Laflin quasi-particle do not have fractional charge. But as you impose global charge conservation, your Laflin quasi-particle can carry fractional charge, right? But you can remove that global charge conservation by putting superconductor on top of fractional quantum Hall effect, but the topological order is still preserved, but the fractional charge disappears. Yeah. So what is a Dirac magnetic monopole? In the context of magnetic monopoles, these magnetic monopole in quantum spin ice, U1 quantum spin liquid is analogous to the Dirac magnetic monopole. It's a dual object. So there's this guy spin-on. While spin-on has a classic analog, but the magnetic monopole do not. It's this topological defect of the U1 gauge field. So this spin-on. So this confinement deconfinement transition. So why is the confinement transition? The reason is the system develops some kind of IC magnetic order by forming this 2-in-2 magnetic order. So you can no longer separate these spin-ons, separate the defect tetrahedral along the pathway without costing too much energy. So as you try to separate these spin-ons, each time you move this spin-on apart, you flip a spin along this pathway, and each time you flip it, it costs finite energy. And this energy grows linearly with the length along this the length of this string. So the energy cost will be linearly proportional to the length of string. So the spin-ons are confined. So you cannot do this separation anymore. So this transition, this magnetic order transition, out of a U1 quantum spin liquid of this type, must be a confinement deconfinement transition. So using this observation, one can do this beautiful, electromagnetic duality. I don't have much time, but just let me illustrate the idea. So you can do this electromagnetic duality to try to, derive this field theory, which is the example of deconfined quantum criticality. And there is an interesting translational symmetry fractionalization of these monopoles hopping on the dual diameter lattice. Yeah, let me just quickly go through this. This is once you do that, you can condense the monopoles and find the proxy magnetic order. And turns out the magnetic order we found by condensing magnetic monopoles, by proliferating magnetic monopoles, by studying the instability of this U1 liquid, the magnetic obtained by doing this is the right magnetic order that being observed in the neutron diffraction measurement. So that's the local moment part. let's focus on the let's focus on the let's turn on the interplay between conducting electron and the local moment, and let's focus on the ordered one, which is easier. There's no fractionalization. There's no exotic phenomenon. Just focus on the ordered side, ordered sample, where the system developed this 2 in 2 out spin-ice magnetic order. So, as I said, this material is rather complex. You got a conducting electron, and conducting electron band structure has been observed by this angular reserve photon emission. Different experimental probes is sensitive to different kinds of degrees of freedom. So angular reserve photon emission measurement only sensitive to conducting electron. For the local moment, it's this particular what I call the Merkel-Hockenberg-Ginger spin-ice state, which they study numerically in a dipolar spin-ice and find this magnetic order in a different context. So this is the example of 2 in 2 out spin-ice manifold order. So this has been observed by neutron diffraction. So neutron see the local moment. So angular reserve photon emission see the band structure of conducting electron. So now we want to combine these two experimental results together and ask what's the consequence, right? We want to synthesize these two pieces of experimental information, from different experimental groups with different probes and ask what's the consequence, right? This is really based on the experimental result and ask what's the next, right? So before I do that, let me make a digression to motivate some thought, a general thought behind, right? So this is this famous result, the quantized numbers Hall effect, was quoted in 2016 Nobel laureate Nobel Prize some introduction. So this is discovered by Qi Xue's group from Tsinghua University in Beijing. He's the experimentalist. His group introduced chromium doping to the bismuth selenium sample. It's a famous three-dimensional topological insulator. On the surface of a three-dimensional topological insulator, there is a time roll symmetry protected Dirac cone, right? So now if you introduce dopant, like magnetic dopant, like chromium, so the system of the local moment of the chromium form a ferromagnetic order. Form a ferromagnetic order. So ferromagnetism enters and break time roll symmetry, and the Dirac cone of the surface Dirac cone will be gapped, right? So the combination of trivial simple Dirac electron coupled with ferromagnetism, you get a gapped spectrum. And if you tune your Fermi level to be chemical potential to be in the middle of this conduction band and valence band, and it turns out the valence band has a non-trivial Chen number, has a Chen number equal to 1. So then you will observe an integer, quantum Hall effect. You get a quantized anomalous Hall effect. This realizes the original idea of Duncan Haldane, where he tried to realize quantum Hall effect without a magnetic field. So this is an example of realizing, quantum Hall effect without magnetic field. This is what they call the quantized anomalous Hall effect. So what I just described is the conventional understanding. Really, this is an example, a very special and interesting and simple example of how conducting electron, interact or interplay with local moment. In this particular context, so the conducting electron is a simple Dirac electron, and the magnetism is a trivial ferromagnetism. Both of them are rather simple, but if we put these, simple Dirac electron with this trivial ferromagnetism, you obtain this remarkable phenomenon of quantized anomalous Hall effect, right? So in our context, the conducting electron is a crystalline symmetry protected, Luttinger semimetal, and the local moment is this complicated 2 in 2 out non-collinear, spin-ice, magnetic order. So both of them are kind of non-trivial. If you put them together, the outcome has to be even non-trivial, even more non-trivial. So it has to be something non-trivial. So it turns out, in fact, that many materials and systems belong to this category of physics, where the local moment and the conducting electron, when you put them together, a lot of interesting phenomena happen. And so today I'm just talking about one very special singular example how this conducting electron play with the local moment. So this is the energy scale For the remaining 10 minutes, let me just sketch the. I have explained the thought. Now I just sketch the details. What's the detail? So this is the praseodymium particle. This is iridium particle. On each iridium particle, there is a praseodymium local moment sitting in the center, and coupled with the neighboring iridium sites. So the dominant energy scale in the problem would be the conducting electron, hopping conducting electron spin orbit coupling, and the correlation between them. And the lowest energy scale in the problem would be the exchange interaction between the local moment. That would be like 10 out of 10 Kelvin. In between, there is a so-called condo-like coupling between a local moment and a conducting electron. So this is what I call FD exchange. So one probably see this many times. In the talk about guitar materials. If you put the iridium in an octahedral environment, you split it into EG and T2G, put 5 of them, you get the so-called J equal to 1/2. You can build up some tight binding model. Although the correlation would renormalize the bandwidth, you can still build up a tight binding model because this material is always metallic. You can build up a tight binding model with a renormalized hopping parameter in the very beginning. So then you can capture the correlation physics from the very beginning, right? So, but at some time still preserve this correlated band touching in certain parameter regime. So this is the local moment physics. This guy is a non-Kramers doublet. You got two F electron, and the spin and orbit are entangled for this J equal to 4. And on the crystal fields, you get a so-called non-Kramers doublet, and they have special property on the time reversal. Only the Ising component, local Z component, is magnetic, and only Z component would couple to magnetic field, also coupled to the conducting electron spin density. Yeah, SungBin and his collaborator, the whole collaborator has actually studied how this transverse component coupled with the conducting electrons. Here, because since I'm magnetic, we study the magnetic order, so we don't worry about this component of coupling. We focus on this Ising coupling instead. Yeah, so this is the coupling we wrote down. We only consider the Ising component. More general coupling has been considered in SungBin's paper in 2013 or 2012. Yeah. So now we started some phenomena. This is the modeling of the microscopics. So before we're doing the heavy calculation, so the system developed magnetic order. We use this magnetic order as the input condition, to this model, and ask how does this conducting electron reconstruct its band structure in the background of this particular magnetic order being discovered by experiments. So this is the magnetic order being discovered by neutron diffraction, and it turns out this magnetic order has a very special property. Although it breaks time reversal symmetry for obvious reason, it breaks time reversal, and it also breaks translation symmetry. The crystal cell has been doubled, right? So originally this tetrahedral is equivalent to this one, just by a lattice translation. This is identical to this guy, but because of the presence of magnetic order, this is no longer equivalent. Look at this spin. This spin is in, and this spin is out. So it's no longer equivalent. So the magnetic cell is twice larger than the crystal cell. But if you combine translation and time reversal, the system stays invariant. So if you translate this spin, this unit cell, this tetrahedral to here, and then doing a spin flip, the system stays invariant. So the combination of time reversal and the translation has been preserved. So this is the antiferromagnetic transformation. This is actually similar analogous to the magnetic translation for Néel state in a cuprate antiferromagnet. If you translate this spin to here and doing a spin flip, the system stays invariant. Okay? So this is a three-dimensional non-collinear magnetic order. It's hard to visualize this symmetry, but this symmetry is there. And because of this symmetry, this symmetry involves anti-unitary time reversal symmetry and translation. So because it's anti-unitary symmetry, so the Kramers theorem, the original Kramers theorem has been modified because of involvement of this lattice part. So all the other, this is the reconstructed band structure in the presence of the magnetic order along high symmetric momentums. Originally has a gamma point in the band touching, correlated band touching. Now a 4-fold degeneracy. Now because of this magnetic order, this magnetic order of the local moment is being transferred to the conducting electron through the internal FD exchange between the local moment and the conducting electron. So the conducting band structure will inherit the symmetry property of the local moment magnetic order. So originally it has a 4-fold degeneration at the gamma point, protected by the cubical lattice group. Now it's no longer there. Got a 2-fold degeneracy at the gamma point, at the A point, and R point. So this 2-fold degeneracy is protected by this modified Kramers theorem because of this T tilde. This T tilde at a certain time also invariant momentous, T tilde squared still equal to -1. So you still got some kind of Kramers theorem, right? It's not it's not equivalent to the original one because now we have this lattice part being involved. So that will pick up a certain momentous, right? So this is the symmetry protection. This degeneracy is protected by this particular symmetry, right? But this symmetry is very fragile. If you apply magnetic field, it will immediately destroy this symmetry. You will no longer have that symmetry. In addition to this symmetry protected nodes, there is also a bunch of Y nodes near the Fermi level. The reason why you have these Y nodes is because this quadratic band touching Luttinger semimetal is the mother state of many topological phases. If you break time also, you can automatically generate these Y nodes. You can, if you get a band inversion, you get a 3-dimensional topology inside. Yeah. So this Luttinger semimetal is the mother state of many interesting things. Now we talk about this magnetic control of the topological band structure. Imagine you apply field to the system, right? For a system with local moment and a conducting electron, the conducting electron form Fermi surface, right? The local moment are localized, and if I apply field, the predominant effect is the Zeeman coupling to the local moment, not to the coupling to the conducting electron. The reason is there are much more local moment than the electrons on the Fermi level, on the Fermi surface. So the dominant effect is the coupling to the local moment. So because the energy scale between the local moments are pretty low, you can easily modify the magnetic state by coupling to the external magnetic field. So this is the example how you apply the field along one direction. So then you can change the state from 2-in-2-out the finite Q into 2-in-2-out the 0Q into 1-in-3-out the 0Q. You can change the magnetic state. And this actually has been observed by Nakazuchi. And then for different magnetic states, different magnetic state of the local moment. So the background provided by the local moment is for the conducting electron is different, right? You have different magnetic background for the conduction electron. For instance, if you take this state and look at the band structure of the conducting electron, so the band structure of the conduction electron is being reconstructed in a different way. Now there is no degeneracy at the gamma point anymore, but there is this emergent wire band touching, which is protected topologically at here. And this is actually a double wire semimetal. It's not a single. It's not a conventional wire nodes. This wire node has a quadratic dispersion along 2 momentum directions and linear dispersion along 1 direction. This is a double wire node. It also has this enormous Hall effect if you measure the Hall effect. Yeah. So you can apply field along other 001 direction. You can have different magnetic state. You can have different band structure topology for the conducting electrons. And this is the comparison between the band structure or the band structure property of the conducting electron without magnetic field and with magnetic field for field along one direction. So this property is not a property in the same parameter regime. So in the whole region from 0 to 0.6, this is all semimetal. But for this plot, only 10% of that is semimetal. So imagine the system is here, then you apply a field. You can drive the system from semimetal to an insulator. So you can have a metal inside transition tuned by external magnetic field. So that means you can use this as a switch, right? So if you apply field, then originally it's a metal, right? Now it become an insulator. So you stop the current flowing by applying magnetic field. Yeah. So let me summarize. So we predict how this band structure reconstruction of the conducting electron by this local moment magnetic order, and predict some symmetry protected and topological protected vinyls and Dirac metal. And take-home message is these hybrid materials with both conducting electron, both iterminating electron, and the local moment can be a quite interesting direction of research for the topological phenomena, for the collision physics, for the band structure engineering. Yeah, thanks very much for your time. Yeah.
Thanks, Gang. Any questions?
Thanks for the very interesting talk. To detect the electronic band structure, since RPES is not very compatible with applied magnetic field, but some materials, magnetic order, can be sensitive to like uniaxial pressure and that kind of thing. So do you expect that to be able to replace magnetic field as the tuning method?
Oh, that's a good point. I think that can happen. Can be done too. Yeah. Besides, as I said, RPES may not be good for the magnetic for the study of the band structure on the magnetic field. But other methods like a transporter magnetic transporter can be very useful and also very interesting. Either whole low XX, low XY measurement can be very helpful.
So often when magnetism comes along, you open up a gap, right? But in this case, your quadratic band touching goes to this while node, right?
Yeah.
So is there some reason, some symmetry reason or something that it should not open a gap?
Yeah, so this is experiment, right? So if there is magnetism, before you turn on the magnetic field, in the presence of this particular magnetic order, because this order has this particular symmetry, so they give you a protection of band touching over here. So this is protected by this magnetic translation. But if you apply field, this symmetry is absent, is no longer there. So then you will not have this band touching here in the presence of field. But you have this band touching at some other non-generic points, right? Non-highly symmetric point.
Any other questions? Comments? If not, let's thank Gang again.